The biggest black hole has officially been measured, and its brain-melting size absolutely defies everything that science previously thought possible. This behemoth black hole is billions of times the mass of our sun, and this brain-melting reality doesn't just defy conventions, it's so unusual that it may force a rewrite of our entire understanding of the universe. That's going to be a lot of work, isn't it? From existing models of the Big Bang to how the Milky Way and even humanity came to be, it's all being called into question. Nothing is certain at this point, and the most qualified astrophysicists in the world are poring over the mystery as we speak. In the meantime, we can look at the mounting evidence, draw our own conclusions, and consider if this is perhaps one of the most significant shifts in astronomical science in decades. Alright, as to what the black hole is and where it came from, we'll cover what is known and what isn't. Though if we're lucky, the ultimate answer may come from CERN, who are, as it turns out, attempting to create artificial black holes in the Large Hadron Collider. And don't worry, it's not as insane as it sounds, despite what everyone was going on about a few years ago. No, it's not going to cause a black hole that's going to end the world. Calm down. Now, celestial configuration, referred to as the Cosmic Horseshoe, that sits about 5.6 billion light years away, and it's now confirmed to be home to one of, if not the biggest black hole ever discovered. The spectacular Cosmic Horseshoe was first identified in 2007, but it's only more recently that a research team at the Institute of Physics, located at the Federal University of Rio Grande do Sul, has successfully measured it. The research team, led by Carlos R. Melo Carneiro, published their observations in the monthly notices of the Royal Astronomical Society, and to put it mildly, the paper has been making some serious waves. The bottom line is that the newly measured black hole isn't just big, it's so big that it's kind of threatening to upend astronomy. Some astrophysicists are leading the charge already, suggesting that it is time to reconsider the current model of the universe. But don't worry, we will get to whether they are just jumping the gun or whether they're seeing the writing on the wall. Now, there's a lot to unpack here for all of this to make sense, so stick with me while we provide a little bit of context. The black hole, first and foremost, doesn't currently have a simplified name, so for now it's called SDSS J1148 plus 1930, or alternatively, because this is oh so much better, LRG 3757, as after the galaxy it was found in. To keep it simple, we'll just refer to it as the Big Black Hole for now, and refer to the galaxy that it was found in by its nickname of the Cosmic Horseshoe, because I don't want to constantly read those numbers over and over again, it's boring and hard. The Big Black Hole was measured as having around 36 billion times the mass of our Sun, meaning that it falls into the scientific category of ultramassive, coming after the supermassive category. Ultramassive loosely refers to black holes with a mass 10 billion times our Sun or more, though the official masses of black holes are a squirrely topic that is something we'll come back to. What makes the big black hole so unusual is not just its size, but how its size relates to its predicted age. Simply put, the common understanding is that black holes grow with age, expanding as they consume mass in their immediate vicinity. We'll also get to that equation in a moment, but for now, the takeaway is that the big black hole's size seems to indicate that it's so old it must have somehow been around before the first stars. That's an implication that flies in the face of the existing timeline of the Big Bang, with common understanding being that a black hole is the remaining core of a dead star. What we have then is a serious question about our understanding of black holes themselves, and our understanding of how stars and galaxies are formed. Or, to put it another way, it's a classic chicken or egg dilemma, with the confusing implications being that somehow black holes came first, and it was their formidable presence that created galaxies in the first place. Interestingly, if it was black holes that came first, the universe would make actually a great deal more sense. As to what created the black holes, well, I guess that's kind of what we're here to discuss, isn't it? But let's not get ahead of ourselves. First, let's establish what is understood about black holes before we investigate if our existing model of the universe needs a bit of a rewrite. What is a black hole? Einstein famously doubted that something as absurd as a black hole could ever exist. Although his general relativity model predicted such a bizarre anomaly, he argued that a singularity, or a point where physics breaks down and creates infinite gravity, couldn't manifest in the real world. He wasn't the only one who had serious doubts, with astrophysicist Arthur Eddington in 1930 being quoted as saying, "I think there should be a law of nature to prevent a star from behaving in this absurd way." It turns out that the universe is far more bizarre than both of these guys assumed, and indeed if a star 20 to 25 times the mass of our sun, it's really big, burns through its fuel, the core collapses under its own gravity. A supernova explodes off the outer layers, and what we get is a dense mass that warps space and time into an absurd gravity well. A black hole formed in this way is referred to as a stellar black hole, appropriately, and it's the one that you are most familiar with. There is actually another kind of black hole that is less commonly discussed, and it may be the explanation for our big black hole. Primordial black holes are hypothesized to have formed during the first seconds after the Big Bang, with the chaotic conditions at the time potentially providing pockets of hot material dense enough to spontaneously collapse gravity. Black holes created in this way would have varied dramatically in size, and chances are most would have dissipated soon after springing to life. Those that survived, however, may have gone on to consuming for billions of years, and were perhaps even the catalysts that created the stars, planets, and the universe as we know it. Now, as we've said many times in this video, we'll come back to that in just a moment, but first we need to clarify a few more details and dispel a few misconceptions, starting with the idea that a black hole behaves like some sort of giant cosmic vacuum cleaner. While black holes do have incredible gravity, they still behave only as their mass allows, and not in a manner that is somehow supernatural, as science fiction sometimes depicts. A good example is that if you switched out our sun with a black hole of equal mass, although it would be a lot cooler, our solar system would continue to function exactly as it does right now. Which is to say, black holes are unique because their gravity is created by incredibly dense mass, not for creating gravity that is somehow unusual or different. Now, planets and stars orbit black holes relatively peacefully for the most part, and in this regard, a black hole plays an essential role in the structure of galaxies. The general consensus is that a supermassive black hole lies at the center of most, if not all, galaxies, and if you didn't already know, we happen to have one at the center of the Milky Way, although you're watching a fairly nerdy science channel, so you probably knew that. Identified in 1974 and named Sagittarius A star, the Milky Way definitely wouldn't exist without it. The big black hole, incidentally, that's about 10,000 times the size of Sagittarius A star, which itself is about 4 million times the mass of the Sun. It's in the big black hole. It's really, really big. There's also a perception that black holes do nothing but consume, and while they certainly do consume and grow as they gorge themselves on anything unlucky enough to get too close, they're also key in seeding new stars. Gas, dust, and other particles are drawn in by a black hole's gravity, and over time, as this enormous cloud gathers, stretching vast distances, it may become a breeding ground for new stars. Meanwhile, the gathered gas and dust that gets close enough to the central black hole is subjected to increasing gravity, and even as the clouds start to fall into the well, it's churned up and superheated, creating an intensely radioactive accretion disk. According to Professor Thomas Collette from the University of Portsmouth, co-author of the paper on the big black hole, quoting him, "Some of this matter grows the black hole, but lots of it shines away in an incredibly bright source called a quasar. These quasars dump huge amounts of energy into their host galaxies, which stops gas clouds condensing into new stars." End quote. As Professor Collette said, this formation of a black hole with a surrounding accretion disk is referred to as a quasar, a type of active galactic nucleus. Relating to the big black hole, a quasar is just part of the life cycle of a black hole, and if all nearby matter is consumed, at least for the time being, a black hole falls into a state referred to as a fossil. The big black hole is a fossil, and this gives some indication of how long it must have been around, also taking into account its size. Now, speaking of its size, let's establish just how big an ultramassive black hole is, relatively speaking, comparing it first with the already mentioned primordial black holes. A primordial black hole, created seconds after the Big Bang, is thought to have originally been the size of a single atom, but with a mass equivalent to a large mountain, according to NASA. A typical stellar black hole will be, on average, about 20 times the mass of our Sun and occupy a space of around 15 kilometers. Then we have supermassive and ultramassive black holes, having up to millions or even billions the mass of our Sun and occupying a space of 4 million kilometers or much, much more. The obvious question now is whether these oversized black holes could have consumed enough surrounding mass to be the size that they are versus how long they've existed. If they originated as stellar black holes, they would logically have been born after the first stars, taking into account that the first stars are thought to have manifested between 100 to 400 million years after the Big Bang. The first black holes would then have formed around that same period, and the short answer is that no, the timelines don't seem to add up. According to astrophysicist Dr. Ethan Siegel, when you looked at galaxies today, you find a correlation between how much mass is in the form of stars within the galaxy and how heavy the supermassive black hole is. End quote. Now, to be clear, the accepted ratio of surrounding galaxy mass versus black hole mass is 1,000 to 1, making this the benchmark of what is standard in the universe as it is today. Dr. Siegel continues, quote, "Then, when you look at galaxies at earlier times, you'd expect that the correlation would remain the same for some time before tilting at earlier times to favor more stellar mass and lower supermassive black hole mass. When compared with galaxies found more locally, the team of scientists found that its black hole is much more massive than its central stellar velocity dispersion would indicate. Additionally, the black hole appears to be overmassive compared to the total stellar mass of the galaxy. What we find, remarkably for the earliest galaxies of all, going all the way back to just 420 million years after the Big Bang, is that nearly all of the ones with black holes display overmassive black holes. In other words, early on, overmassive black holes are actually typical. This is interesting and highly suggestive of the notion that black holes, and not stars, came first." End quote. Let's just clarify that what Dr. Siegel is saying is that not only do black hole timelines not add up like they should, it often seems like the youngest black holes actually tend to be the biggest. More to the point, many observed supermassive and ultramassive black holes have a ratio of 100 to 1 or even 10 to 1 despite not having had appropriate time to consume nearby mass. This isn't just a small discrepancy, it's the sort of deviation that suggests something somewhere is being completely misunderstood. The question overwhelmingly becomes then, well, what created these black holes if not stars? Unraveling the mystery. Now, if you're expecting a definitive answer that clears all of this up, I've got some bad news for you. There isn't an answer. This is an ongoing mystery. We haven't cracked it here at Celestium. I'm so sorry. And depending on who you ask, you're going to get a very different explanation. What we can do is join in the ongoing discussion and explore some of the hypotheses and other potential explanations. The first factor we have to take into account is that detecting and accurately measuring black holes is notoriously difficult. It is, in fact, impossible to even directly see a black hole given that they don't reflect or emit light, meaning that even determining that one is present can be incredibly challenging. This may come as a bit of a surprise given that we've shown plenty of images of black holes in this very video already, but rest assured that what you're seeing is an elaborate composite made up by a planet-spanning network of radio telescopes. When combined, the network is referred to as the Event Horizon Telescope, and the radio wave data provided is processed by a supercomputer to generate the images that you see. It was the Event Horizon Telescope that imaged our own supermassive black hole, Sagittarius A star, and this only occurred for the first time as recently as May 2022. You probably remember the news. Notably, the image you see is showing the accretion disk around Sagittarius A star as opposed to the black hole itself. Now, with that in mind, and the added context that researchers are essentially studying something that's not only invisible, but also often billions of light years away, how can we be sure that any black hole information that we have is actually accurate? And the short answer is that we actually can't. Part of the reason that the big black hole is so revolutionary is that the information gathered regarding its measurements is thought to be unusually accurate. A new technique was pioneered for the study that made use of multiple sources of data combined into a more precise model than ever before. The data set included information from the Multi-Unit Spectroscopic Explorer, or MUSE thankfully, because that was a mouthful, plus high-resolution images from the Hubble Space Telescope. This was combined with information derived from the unique gravitational lensing effect of the Cosmic Horseshoe, plus stellar kinematics. We actually went into a bit more detail on gravitational lensing in our recent Gravity is Weird video, so do check that out if you want more details. Stellar kinematics, meanwhile, that's the measurement of how orbiting astral bodies are influenced by the black hole. And in this case, it was found that nearby bodies are moving at around 400 kilometers a second, or 13 times faster than the Earth orbits the Sun. General consensus is that measurements of the big black hole are accurate enough, meaning that we can rule out any of the perceived anomalies being miscalculations or human error. On that note, a previous black hole, TON 618, was estimated to be 66 billion times the mass of our Sun, occupying a space 30 to 40 times our entire solar system. That estimation was later revised to 40.7 billion, and even that number is still debatable. This should make clear just how vague cosmic estimations can be, as explained by Professor Collett, quote, "Most of the other black hole mass measurements are indirect and have quite large uncertainties, so we really don't know for sure which is biggest. However, we've got much more certainty about the mass of this cosmic horseshoe black hole thanks to our new method." End quote. Okay, so let's assume that measurements of the big black hole are accurate and move on to the first potential explanation of why it's so big and how it became so big. An explanation that has some support is that what we're seeing isn't a single black hole, but rather the result of a number of black holes that have merged to create the behemoth that we see today. The idea is that over an incredibly long period of time, multiple stellar black holes and perhaps even some primordial black holes drifted toward one another, and in what must have been an extremely violent cosmic event, well, they joined together. Professor Collett explains, "It is likely that all of the supermassive black holes that were originally in the companion galaxies have also now merged to form the ultramassive black hole that we have detected. So, we're seeing the end state of galaxy formation and the end state of black hole formation." End quote. Details that support this include the already mentioned factor that the big black hole is a fossil, having already completely consumed anything in its immediate vicinity. If this included other black holes, we don't know for sure, but it does seem like a pretty logical explanation. Another hypothesis is that supermassive and ultramassive black holes are primordial black holes that survived the early Big Bang, remained stable, and have been drifting through the universe ever since. This also seems like a logical explanation, but it is one that is very difficult to definitively prove one way or the other. Though finding an answer may not be a case of addressing the overmassive black holes directly, but rather by demonstrating in the timeline of the universe that they must have been present since the very beginning. Professor in the Department of Physics and Astronomy at Johns Hopkins University, Joseph Silk, is taking this approach. The highly respected and award-winning astrophysicist said in a recent paper published in Astrophysical Journal Letters, quote, "We know these monster black holes exist at the center of galaxies near our Milky Way, but the big surprise now is that they were present at the beginning of the universe as well, and were almost like building blocks or seeds for entire galaxies. They really boosted everything, like gigantic amplifiers of star formation, which is a whole turnaround of what we thought possible before, so much so that this could completely shake up our understanding of how galaxies form." According to Professor Silk, taking into account that black holes existed far earlier than previously thought adds a piece of the puzzle to existing models, creating a much clearer picture of how the universe actually formed. He doesn't make any hard assumptions as to where the black holes came from, but insists that they're needed for our existing model of galaxy creation. He continues, quoting again, "We're arguing that black hole outflows crushed gas clouds, turning them into stars and greatly accelerating the rate of star formation. Otherwise, it's hard to understand where these bright galaxies came from because they're typically smaller in the early universe. Why on earth should they be making stars so rapidly? We can't quite see these violent winds or jets far, far away, but we know they must be present because we see many black holes early on in the universe. These enormous winds come from the black holes crushing nearby gas clouds and turning them into stars. That's the missing link that explains why these first galaxies are so much brighter than we expected." End quote. Now, the brightness Professor Silk is referring to is the quasar activity we discussed earlier, and he's addressing the fact that the earliest galaxies, bizarrely, often seem to have the most activity in this regard, despite supposedly having the smallest black holes. It's a separate anomaly Professor Silk is tying in with the possible presence of early, massive black holes. Professor Silk goes on, "We thought that in the beginning galaxies formed when a giant gas cloud collapsed. The big surprise is that there was a seed in the middle of that cloud, a big black hole that rapidly helped turn the inner part of that cloud into stars that are age much greater than we ever expected. And so the first galaxies are incredibly bright." Now, Professor Silk's argument is far from being confirmed, and there is still very much an ongoing discussion, but the answers may be forthcoming sooner than you might expect, with the golden era of technological advancement just on the horizon. From the extremely large telescope to CERN attempting to artificially create black holes, things really are about to get very interesting. The precipice of discovery. Now, it may seem like the research paper on the big black hole only served to raise more questions than it answered, but don't take for granted the incredible new technique the team pioneered to take accurate measurements. That the study was done on a dormant black hole is in itself groundbreaking, with previous observations having largely relied on detecting quasar activity as opposed to the black hole. As research lead author Carlos Mello put it, the discovery was made for a dormant black hole, one that isn't actively accreting material at the time of observation. Its detection relied purely on its immense gravitational pull and the effect it had on its surroundings. What is particularly exciting is that this method allows us to detect and measure the mass of these hidden ultramassive black holes across the universe, even when they are completely silent." End quote. The detection method is certainly a breakthrough, but it's nowhere near as precise as the black hole observations that will soon be made with the aptly named Extremely Large Telescope. The ELT is said to be one of the biggest revolutions in astronomy history, with one of the already established goals to provide more precise measurements on supermassive and ultramassive black holes. For context, the ELT will gather more than 100 million times more light than the human eye and is equipped with roughly 250 times the light-gathering area of the revolutionary Hubble Space Telescope. The result will be images 15 times sharper than have been produced up to this point, including of distant black holes. It's certainly something to look forward to, and there's no question that we'll be closer to making sense of some of the ongoing cosmic mysteries. Be prepared for a wait, however, as the ELT is only due to be finished in 2029. Meanwhile, you may be interested to know that the European Organization of Nuclear Research, otherwise known as CERN, is actively trying to birth quantum black holes using the LHC. The story made headlines a few years ago, as I said, though the focus of media coverage at the time was on whether CERN would suck our galaxy into a gravity well. Let's clarify that no, they're not trying to do that. CERN hasn't succeeded in their task yet, but should they get results, it would imply that supermassive and ultramassive black holes are indeed primordial black holes that survived the first seconds after the Big Bang. We'll update if there's any breakthroughs in this ongoing research, but for now, thank you for watching.